The graph of this rational function here has a hole at x minus 1 over x minus 1 does reduce, and the hole is at whatever makes this factor 0. So x equals 1. It has an even vertical asymptote at x equals 2, because 2 would make this denominator equal to 0, and this factor x minus 2 is to the power of 2, so it's an even vertical asymptote. X minus 4, or x equals 4, is an odd vertical asymptote because this factor is to an odd number. Even and odd vertical asymptotes are very helpful because of their graphical representations and can help us to understand more about what's happening to the left and right of a vertical asymptote. If you have an even vertical asymptote, your left and right behavior is the same, both to infinity or both to negative infinity. And if you have an odd one, the behavior on either side is opposite. You have seen examples where a limit does not exist at a vertical asymptote, and those limits can be expressed as infinite limits, such as infinity or negative infinity. And we did one of those in 1.4. Let's go ahead and evaluate some limits at vertical asymptotes. X minus 2 does not reduce. It's definitely a vertical asymptote, but we're checking for when you're approaching it from the right side. So a number to the right of 2 is 2.1, and I'm going to plug in 2.1. Because I know this is a vertical asymptote, I'm just looking for, is this headed toward positive infinity or is it headed toward negative infinity? That's the same as 5.1 times 10. So where are we headed? Toward positive infinity. If your limit is infinity, technically the limit does not exist because infinity is not a number, but we're going to write infinity instead of does not exist because we want to give a picture of the limit behavior. This is the exact same function, but it's asking for 2 from the left, so I could plug in 1.9, or I could remember that x minus 2 to the power of 1 is an odd vertical asymptote. So if the right side goes to infinity, the left side will go to negative infinity. Odd vertical asymptotes have opposite behaviors. Here we have an even vertical asymptote at 1. So when we're approaching 1 from the right, I'm going to plug in 1.1. When I plug in 1.1, I get negative 900, so that is headed toward negative infinity. This is the same function, same vertical asymptote at x equals 1, and it's an even vertical asymptote, so the left-hand behavior is equal to the right-hand behavior. So they're both going to go down to negative infinity. And if the right-sided limit matches the left-sided limit, then the limit, not a one-sided, but the limit, is also equal to that. Here we have x minus 2 is it a vertical asymptote? Actually, I think we can factor the top and reduce, and this, instead of being a vertical asymptote, will be a hole. Always look for the option to factor because this denominator restriction may be a hole instead of a vertical asymptote, and with some algebraic manipulation, we can end up just using direct substitution to evaluate our result. Limits at infinity can also be described as the end behavior of a function. That means that if a rational function has a horizontal asymptote y equals L, the limit at infinity of that function is L. Informally, when evaluating limits at infinity, consider only the terms of highest degree in the numerator and denominator. If I'm evaluating a limit as x approaches infinity, I'm not really concerned with infinity subtracting 1. Okay, that's just infinity. And I'm not really concerned with plus 1 either. I'm really concerned with the variable of highest degree in the numerator and the denominator. So this is an equivalent, basically an equivalent limit to x squared over x squared because we're approaching something so massive that the -1 and +1 are basically not relevant. Now we can reduce the limit of a number as x approaches anything is that number. And if you noticed, our degree of the numerator and the denominator was the same, so our coefficients should be our horizontal asymptote, which means, yes, our limit as x approaches infinity goes to 1, our horizontal asymptote. As we're headed toward negative infinity, we really only care about terms of highest degree because those are the most relevant for infinity. We have a horizontal asymptote, and as you know, a limit as x approaches infinity is also referring to the end behavior. So the horizontal asymptote will be your resulting limit. Here it looks like, yeah, we're not going to get a number. We're going to get infinity or negative infinity. If I plug in infinity, then I get infinity. Same function, so same equivalent. But now I'm plugging in negative infinity, and I get negative infinity. Rational functions have at most one horizontal asymptote. However, radical functions frequently have two horizontal asymptotes. Find the following. We only care about terms of highest degree when we are evaluating limits at infinity because infinity is so massive. And here, even though we have a radical, we're going to take the term of highest degree, which is still under a radical, and the term of highest degree in the denominator. The square root of 4 is 2. The square root of x squared is absolute value x. Because the x had been squared, it doesn't matter when you're square rooting, it will automatically be the positive version. Now this 2 I can take out of the limit and end up with this absolute value function, which is a piecewise. In pre-calculus, you learned that absolute value x over x, or the reciprocal, when x's are less than 0, you're going to get a -1 as your result. When x's are greater than 0, you're going to get a +1 as your result. So as x approaches infinity, we are approaching x is greater than 0, so my result is 1. The limit as x approaches infinity of absolute value x over x is just 1. 2 times 1 is 2. This is the same function, just asking as x approaches negative infinity. So it will be 2 times the limit as x approaches negative infinity of absolute value x over x. And this time we're approaching negative infinity, so we're looking at the x is less than 0, and the result of that is -1. So this is -1, and our resulting limit is -2.